Today we're going to talk about resonance, a phenomena where existing oscillations are continually reinforced so that their amplitude grows over time. Once we've covered the basics of how resonance occurs in the first place, we'll then also go on and talk about some applications from considerations in structural mechanics to children's games, music, and sound in general. As with any good lesson, let's start with a demonstration.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw, then it's more obvious.
So what's happening here? The straw gets tossed side to side, but I can't see why.
Let's record it while I crank the volume. Alright, I took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Wow.
This is a lot like a swing. In this case, the glass is behaving like the swing, and the sound is behaving like whoever is pushing the person who is swinging. And by pushing someone on a swing at exactly the right moments, at the top of their trajectory, you're putting in more energy into their oscillation, which means they'll go higher and higher every time you push them. Likewise, there's this wave going around the rim of the glass, and every time the sound hits it, it reinforces the oscillation that's already existing, so long as the sound is of precisely the right frequency, just like if you want to push someone higher and higher in a swing, you want to make sure you push them only at precisely the right time. And in fact, the frequency needed in order to make this happen is the same frequency that the glass would make if you were to just flick it.
That's it.
To understand why that is, let's talk about how resonance would occur in a simple string, for example. We've already established that standing wave patterns are produced when two identical traveling waves move in opposite directions past each other, and that an easy way to produce a standing wave is to make use of a reflection. So allow a traveling wave to bounce off of one end or border or boundary of a medium, reflect back in the opposite direction, and the interference of the original wave with the reflected wave will produce a standing wave pattern. And as you may have noticed, I made the reflected wave flipped from the original wave, so that means I'm treating the right hand of the string as a fixed point, so it's being held there in place. And in fact, if you go back, you'll see that the two wave patterns exhibit complete destructive interference at all times at the rightmost point, so our fixed end has to be a node. If we play time a little bit forwards, the reflected wave will reach the end at the left. And now the reflected wave traveling to the left will reflect over the left end, just like the initial wave did over the right. And as long as we continue to generate this initial blue wave, which continues to reflect and become this red wave pattern, which then reflects and becomes the green wave pattern, eventually that secondary reflected wave will also reach the right-hand side of this string. Note that in these time skips, I'm making sure that all three of these wave patterns are traveling the same distance as each other. For example, at the right end, the red reflected pattern is the inverse of what the blue pattern would be if it continued to the right. The blue pattern moving to the right is cresting in the positive or upwards direction, and the red pattern is cresting but in the negative direction. Likewise, on the left side, the green pattern is the inverse of what the red pattern would be doing. The red pattern at the left end is cresting in the downwards direction, and the green pattern is cresting in the upwards direction. I may not have drawn everything perfectly, it's hard to do, but the general gist should be correct. Now, of course, at this point, the green wave pattern will reflect across the right-hand fixed point as well, but let's ignore that for now. Notice that the green and the blue wave patterns are traveling in the same direction. These are both traveling waves moving to the right. But these two waves are a little bit out of phase with each other, which means they're not going to completely constructively interfere. In some places, they'll interfere constructively, but in a lot of places, they'll interfere destructively. When this green pattern reflects over the right-hand point again, it's going to create a wave moving the same direction as the red wave pattern. But it's going to be a little bit out of phase with the red wave pattern. And that means those two patterns will destructively interfere with each other to some extent. And every time this reflection occurs, we get a new wave pattern that's a little bit out of phase with one of the existing wave patterns, which means it's going to exhibit some degree of destructive interference. And when this happens enough, the wave pattern essentially just goes away. Eventually, for every wave pattern moving to the right, there will be a reflected pattern moving to the right, completely out of phase with it. And same for every wave pattern moving to the left. They'll each end up with a pair that perfectly destructively interferes the existing one. This is kind of the opposite of resonance, right? Resonance is the idea that the existing wave pattern is reinforced. But here we're seeing that the existing wave pattern is destroyed upon successive reflection of the wave from one end to the other. To get resonance, we need to make sure that each reflected wave is in phase with the other wave pattern that's already moving in that direction. So how do we make sure that happens? Let's recreate our initial example and see what we can change to make this work. I should specify that the phase that I've drawn here is arbitrary. We could do this at any arbitrary phase of the initial wave, but it will be easiest to see visually what's going on if we start here. The reflected wave is going to be flipped from the initial wave because we're treating this end as a fixed end. This video originally went on about 30 minutes past this point, but this is apparently the last time I saved before it crashed and erased everything. And I'm not redoing all that work. So while incomplete, I am going to upload this, in part because it's actually really hard to find good explanations of why resonance occurs. And a very, very brief summary of the rest of this portion of the video is that if you were to change the length of this string, the reflected waves would always end up in phase with the original waves, producing constructive interference at each reflection. So if you have the right length for your frequency, it will produce constructive interference every time it bounces from one end to the other, which means if you continue wiggling one end, the amplitude will grow and grow and grow as each of the waves continues to add on top of the previous ones, and you continue to supply more of them. When the length of your string is wrong for the frequency or wavelength you're looking at, on the other hand, again, the wavelengths kind of, every time they reflect, they destructively interfere, and it kind of disappears. This is why the glass made a particular sound when he flicked it. He didn't flick it with a certain frequency, he flicked it and he created all possible wavelengths of oscillation within the glass. However, the oscillations with the wrong wavelengths for the circumference of the glass interfere destructively every time they go around in the circle of the glass. Whereas the particular frequencies that are in phase with themselves when they've completed one full cycle around their circumference persist. So when you flick the glass, you create all the different wavelengths. However, only the ones that match the length of the system that you're looking at will actually persist over time because they don't destructively interfere. On the other hand, all the other ones disappear, and that's why something like a wine glass makes a clear tone when you flick it, or why silverware, if you bang it on something really hard, might make a little bit of a tone. So the too long didn't read is that resonance occurs because only a handful of specific wavelengths will persist in a medium upon reflection or going around, for example, in the case of a wine glass, whereas the vast majority of them will destructively interfere as they reflect back and forth or go around and around, disappearing over time. Actually, I'm also going to add in this part because I was just starting to write down a description to go along with this video, and I realized it would just be easier to explain it. So let's watch this, but bear in mind that what you're seeing here is not exactly real. I'll explain after. So this is a guitar from the inside through just a typical cell phone camera. Now, the strings of a guitar never look like this, or even like this. They oscillate as like a whole. So for example, the string at one moment might look a little bit like this, and the next moment it might look like this, and maybe there'll be a little bit of texture on it. But for the most part, that's all there really is. So what's going on here? This happens because of how the CMOS sensor in a typical digital camera works. So rather than exposing the whole image at once, what they do is the first row of pixels is exposed to the image, then the second row, and then the third, and then the fourth, and then the fifth, and so on, all the way down to the very end. And there's a little bit of a delay between each of these, so from one end of the photo to the other, there's actually a time difference. So if anything is happening very rapidly in whatever you're recording, there will be distortion within a given frame. So what you're seeing in this image is actually frequency, even though it looks like you're looking at different wavelengths, right? This looks like a shorter wavelength than this, which looks shorter wavelength than this. But again, the strings themselves are really pretty straight. And the reason why you're seeing that is because the speed of a wave in a guitar string can be, is hundreds of meters per second, sometimes maybe even into the thousands. And so within a given frame, since there can be some microsecond delay from one line to the next, in that time, the string will have moved. And as the different lines of your image are exposed, the string can have moved back and forth multiple times, creating this apparent wavy pattern. So in this case, even though the strings are really just kind of oscillating back and forth as a whole in more or less straight lines, what we're seeing here is the rate at which they are vibrating. And you can see that these skinnier strings vibrate faster than the thicker ones. If you recall from one of the videos from one of the previous lessons, the speed of a wave in a material in a string depends on the tension in the string as well as on the density of the string. And so a skinnier string or wire has a smaller density than the fatter one. The fatter one has more mass to move, and so it tends to vibrate more slowly. As you either have already learned from the rest of the lesson, or you will learn when you get to it, the resonant frequencies depend on the speed of a wave in the medium as well as the length of the medium, the length of the string. In a guitar, the strings all have more or less the same length. But one way to achieve different frequencies and therefore different sounds is to have some strings be more dense, thicker than other ones, and therefore having different wave speeds. Another way to do it is to adjust the tension, and that's what the tuning knobs are on the guitar. You twist it to tighten it or loosen it. So the sound that a guitar string makes is determined primarily by the thickness and density of the string, as well as the tension, which you control just by twisting the little tuning knob. These thick strings that vibrate back and forth slowly make low notes because they only vibrate back and forth slowly, and therefore they push the air slowly, creating a low frequency sound wave, which we perceive as more of a bass sound. On the other hand, a skinny taut string will vibrate back and forth really quickly, creating a higher pitched sound. Again, I'm sorry, this is kind of like rushed and out of order. And this was set up much better in the original video. But yeah, not happening again.